Hello everyone. Welcome to lecture 12 of quantitative trading strategies. So in this video, we're going to mainly talk about the pairs trading using machine learning. All right, so we talked about pairs trading last time. So this is a quantitative trading strategy that involves two highly correlated or co-integrated assets. So in this case, we're going to use some statistical tests to identify two assets that have the long-term relationship. And then our primary assumption is that the spread of the price, right, between these two highly correlated or co-integrated assets will exhibit a mean reversion behavior, right? So in case of temporary markets mispricings, and their spread will diverge. And such divergence will only be temporary. So in the long run, they will revert back to their mean behavior. So we expect the long-term equilibrium relationship to appear in the long term, and the stock prices, the two assets will move in tandem, and any form of deviation is likely to be temporary, right? Only temporary, and this creates the opportunity to generate trading signals. And eventually, these deviations will disappear, and the spreads will revert back to the mean behavior. All right, so there are a few factors that impact the success of a pairs trading strategy. So first one is our ability to find the pair of co-integrated or correlated assets, right? So we need to loop through each pair of assets for a set of assets, and then conduct the statistical test, right? So that's the first factor. The second factor is that can we accurately predict the spread between these two assets, right? So this is a second major component that determines the generation of our trading signals. So for example, we used the moving average in the previous chapter, the previous exercise, and then this is used to standardize the daily spread into a z-score, right? So this is how we obtain from the spread to the z-score. So such a moving average approach actually acts as the predicted spread, right? So we predict the spread is gonna be the quantity, and then we calculate the difference, which is a z-score, a standardized difference. So that's how we use the moving average as a prediction. Of course, this is a very naive prediction, and in this case, we want to use machine learning technique to do the prediction, which will give us more accurate predictions. So the third component is the proper risk management to have this in place, right? So because in case the spread moves in the adverse direction, and it will cause loss to us, so a proper stop loss is often placed upon using this strategy, right? So these are the summary of these three components: the ability to find the pair of co-integrated or correlated assets, the ability to predict accurately the spread time series, and also the proper risk management. All right, so let's talk about what is a machine learning model. So a machine learning model is a predictive function, right? So it's a function that maps a given set of data to a given set of predictions, right? So in this case, we're going to predict the daily spread, and the spreads will then later be used to identify the profitable trading signals. So because the spread is continuous quantity, we're going to explore mainly the task of regression, right? So regression means that the target's outcome is a continuous variable, and we're going to use to explore using three algorithms. One is a support vector machine, one is random forest, and another one is a neural network. We're also going to explore augmenting the feature space, which is also called feature engineering, right? Using the historical time series. So let's decompose a machine learning model. So it mainly consists of two components. So a model it can be thought of as a physical object that has its own size, its own components, right? So the first component is the parameters or the weights. So these serve as the building blocks of the model, right? So these are the building blocks that the model actually consists of. And the model architecture is the second component, and this is specifying how the information is structured together, right? So when we have input data, how they will interact with the parameters, which parameter interact, is it multiply, is it plus, and then together they generate the output. So when we say model training, this is the process of tuning these parameters such that they are optimal in the sense that they give good predictive performance, right? They give good predictions to the test set. And we often expect the model to do well on the training sets, but also more importantly on the test set. So this process, we continue to fine-tune the parameters, and then this will improve the accuracy of the predictions on the training data as iteration proceeds, right? So there's one common phenomenon which is called overfitting. This means that the model performs very well, right, on the training set, but not so well on the test set, right? So it's said to be overfitting the training data. And this is common because nowadays the models are typically quite complex. If the data is not very large, but the model is very complex, then it's very likely to overfit. Right. So in this case, we need to apply proper regularization such that the model is not so overfitted, but it learns to generalize to the test set, which is the future unseen data set. So this is a typical model training framework. Mostly in the context of a neural network, we have training data in the form of input features and target labels. And then we pass it to the model, which consists of the parameters and the architecture, which will give a prediction. And then based on the prediction, we will measure the distance in the form of cost. So we have a cost function here, and then we will come back as a feedback loop, right? So apply the optimization technique and then fine tune the model itself, which is mostly the parameters, right? So usually we would fix the architecture in advance. All right, so that's it for this video, and thanks for watching. I hope to see you in the next video.